SwayamPrabha. Digital India. Educated India.
Hello, in this video we will look at the 3 and the 4 parameter models. We will build upon what we already discussed about the Kelvin and Maxwell model. Using them as the building blocks, we will discuss these 3 and 4 parameter models. So, let us first start with a quick summary of what we have discussed about Kelvin and Maxwell models and highlight what is important for today's discussion. So, these are the constitutive equations or the relation between the stress and strain for the Maxwell and the Kelvin model that we have derived. We have also derived the response under different loads. So, for the Maxwell model we started with creep load, meaning sigma is equal to sigma naught times h of t. So, when a constant load is applied, then we found out the response here. So, when we talk about creep loads, usually we also are interested to know what is the creep compliance. So, what is the creep compliance? It is given by d of t and it is simply the strain by stress. So, in our case the stress is constant sigma naught and the strain is given by this formula. So, essentially we just need to remove this sigma naught term from this creep response, which should give us T by Poisson ratio, which should give us T by viscosity plus 1 by E modulus. Then when we looked at relaxation load, when we said the strain is fixed, then we got the stress response which is given here. So, again for relaxation loads we usually talk about the relaxation modulus. Relaxation modulus represented as E of t is simply the stress by strain. Again here strain is constant, so we will write this epsilon naught. So, this should give us, it is E power minus t by tau, where tau we have already defined is the relaxation time. Sometimes it is also called as retardation time. Okay. So, in addition to the creep and relaxation, we also looked at the constant strain load for the Maxwell model, and here is the response we got for the constant strain applied. So, when we move to the Kelvin model, we only discussed about the creep load. We have not discussed about the relaxation load, because if you recall, we said for a Kelvin model one cannot apply a true relaxation test, which means sudden displacement is not possible, and the reason is because of the damper. Okay. But coming back to the creep load, again we know what is the creep load, where the stress is constant and given here is the strain response. So, for creep load we said we look at the creep compliance, which for Kelvin model is given as 1 by E times 1 minus e power minus t by tau. Again tau here is the relaxation time which we just defined, and this relaxation time is given by viscosity by modulus E. Okay. So, with this quick summary of the Maxwell and Kelvin, let us move on to the 3 and 4 parameter models. So, here we will first start by deriving the stress strain relations for the 3 parameter model, and later we will look at the creep response of the 3 parameter model. But when we move to the 4 parameter model, we will see that there is no need for us to develop these stress strain relations. Instead, we should be able to find the creep response with what we have already discussed. So, let us start with the 3 parameter model. 3 parameter model, as we know, is there is a spring which we call it as free spring E naught, which is in series with a Kelvin model. Kelvin model with a spring and a damper which are parallel. So, the way we will progress is we will consider that we have a spring which is in series with a Kelvin model. So, the spring and the Kelvin are the basic elements using which we will develop the stress strain relations for this Kelvin model. There is another name for the Kelvin model called the White Kelvin model. So, there is another name for this 3 parameter model called the White Kelvin model. So, first let us look at the equilibrium and the constitutive relations. So, equilibrium equation, since we are now considering spring represented as sigma s, stresses in the spring, and stress sigma k here represents the stresses in the Kelvin model. So, both these spring and damper which are parallel together, we call this as the Kelvin model, and the stress is represented as sigma k. So, equilibrium says since both of these are in series, the same stress which is at the ends is experienced by the free spring as well as the Kelvin model. And coming to the kinematic equation, since both of them are in series, the total strain is an accumulation or the summation of the strain in the spring given as epsilon s plus strain in the Kelvin model given as epsilon k. But now let us look at what are the constitutive equations for the spring and the Kelvin, which we have already known based on the discussions from earlier videos. For the spring, this is simply the Hookean model, where we say that the stress in the spring sigma x is given as the modulus times the strain. Coming to Kelvin, here we again recall what we have derived in the previous videos for the Kelvin model. This is just the stress strain relations for the Kelvin model. The only difference is here we have replaced the stress with sigma k, meaning the stresses in the Kelvin model, and strain we are representing using epsilon k, which is the strain in the Kelvin model. And since the Kelvin model is made up of spring with modulus E1 and viscosity nu1, that is what is represented in the formula here. Okay. Now, let us see how we proceed to develop the stress strain relation for this 3 parameter model. First, we will start by introducing a differential operator d. So, we will rewrite this Kelvin equation as E1 epsilon k plus mu 1 times. Here, instead of writing the first derivative of the strain, I will write it as d times epsilon k, where d here is the differential operator. And the interesting part of this is d can follow the rules of algebra. So, what it means is you can do the multiplication, factorizations and other algebra operators with this differential operator d. So, here d represents the first derivative, but of course, when there is a second derivative, it is represented as d square, third derivative as d cube and so on and so forth for higher derivatives. Okay. Now, what we will do is we will try to write this Kelvin equation in terms of strain. So, we will try to bring strain epsilon k to the left hand side of the equation and then rewrite this equation. So, then it will be sigma k divided by E1 plus mu 1 times d. So, since I said that D follows the rules of algebra, I can move D away from this epsilon k. Okay. So, once I have this, now I can rely on the kinematic equation to say that epsilon, the total strain, is summation of strain in the spring plus strain in the Kelvin model. So, first let us see how we can write the strain in the spring. So, from this I should be able to write the strain in the spring is simply sigma s by E naught. So, that I am replacing here, stresses in the spring by the modulus, plus we just wrote epsilon k, or the strain in the Kelvin, which is sigma k by E1 plus mu1 times d. Again, if we recall from the equilibrium equations, we know the total stresses are the same in the spring and in the Kelvin model, which means we can replace this sigma x and sigma k with sigma. So, if I do that, it will be sigma by E naught plus sigma by E1 plus mu1 d. So, what we have done is simply replace the sigma x, sigma s and sigma k with the total stress sigma. Okay. So, now we need to move those in the denominator to the left side of the equation. So, this E naught and E1 plus mu1 d. So, once I do that and multiply with the strain which is on the left hand side, I should be getting E naught times E1 times the strain epsilon plus mu1 times d epsilon. D epsilon is what? It is epsilon dot, or the strain rate. This is sigma times this denominator E1 plus mu1 d, which will give us E1 sigma plus sigma 1 d times the stress sigma will give us stress rate, or sigma dot, plus E naught times sigma. So, this is the relation between the stress and strain, but as we know, there is a standard form we write the differential equations for a viscoelastic material, which is like this. So, usually we start with sigma without a coefficient and then add coefficients to higher derivatives of stress. Since I notice in my equation the derivatives of stress stop at the first derivative, now we move to the right side of the equation where we write the strain terms. So, coefficient times the strain plus another coefficient times the strain rate. Again the strain rate stops at the first derivative, so we stop at Q1 coefficient. So, this we are calling it as the standard form. So, now let us rewrite this equation of stress and strain in the standard form. So, now I notice that if I look at the coefficients of stress sigma, it is E1 plus E naught, that I will take it divide the whole equation with. So, once I write stress here, it will be plus, for the strain rate we have mu 1 divided by this coefficient of the stress, which is E naught plus E1. Now writing the strain, it is E naught E1 by again the coefficient of stress, which is E naught plus E1 times the strain, and lastly the strain rate, the coefficients are E naught times mu 1, again the coefficient of the stress, which is E naught plus E1 times the strain rate. So, this is the constitutive equation of the 3 parameter model in the standard form. As you can see, if you compare this equation with the equations we got for Kelvin model or the Maxwell model, it is a little more elaborate, or it is a little more complex, meaning that later if we want to use this equation to solve for a particular load, solving will not be that easy, it will be a bit tedious. So, we should find other ways to solve this differential equation, or to find the response for a particular load. So, we will see that with creep loading. So, here we are looking at 3 parameter model again with creep load. As we can see, the 3 parameter model is simply free spring and the Kelvin model. So, there is a chance here that we can use superposition. So, since we are applying a creep load, the response we are looking at is strain, and from the constitutive equation we know the strain is simply the summation of strain in the free spring plus strain in the Kelvin. So, which means we can superpose these two creep responses individually for the free spring and the Kelvin model to get our creep response for the 3 parameter model. So, let us first look at what is the creep response for a free spring. If it is only spring, then we can simply invoke the Hooke's law, from which we can write the strain is stress by modulus. This is for the free spring. Now, if we are only considering the Kelvin model, the creep response for Kelvin model we have already derived and is shown here. So, it is written in terms of E1 and tau. What is tau here? Tau is nothing but the relaxation time or the retardation time, which is given as viscosity mu1 by modulus E1. Okay. Now, since we already have the strains in the free spring and the Kelvin, now writing the strain in the 3 parameter model becomes easy. So, because it is simply the sum of the strains in the spring and the Kelvin model. So, if they add them together, this represents the strain in the free spring, and the second term represents the strain from the Kelvin model. So, to summarize, what we have seen here is, instead of solving the differential equations to get the creep response, we have invoked the superposition, where we said the strain is written as a superposition of the free spring creep response and the Kelvin model creep response. Next, what we will do is, we will move on to the 4 parameter model. There we will look at both the 3 and 4 parameter models, and we will visualize how the response looks like. But first, let us derive what is the creep response for a 4 parameter model. So, here in a 4 parameter model, we have already seen that we have a Maxwell model and a Kelvin model both in series. So, this represents the Kelvin model, and the free spring here and the free damper here represents the Maxwell model. Okay. So, again, how do we solve for the creep response here? We follow the same procedure we followed in the previous slide for 3 parameter model, where we showed instead of solving the differential equations, we simply use the superposition, which means we superpose the strain response of the Maxwell model and the strain response of the Kelvin model. So, let us first see what is the creep response of a Maxwell model. So, here we represent the strain in the Maxwell model as epsilon m, which is given in terms of the applied stress sigma naught times mu naught the viscosity of the free damper and E naught the modulus of the free spring. Okay. Next, we will look into the Kelvin model, where we got the strain in the Kelvin model represented as epsilon k is given in terms of E1, the spring modulus present in the Kelvin model, times tau 1. What is tau 1 here? Tau 1 is the relaxation time given as mu 1 by E1. So, these are the viscosity and modulus in the Kelvin model. Okay. So, once we have this creep response of Maxwell and Kelvin, now it should be easy for us to write what is the creep response of the 4 parameter model, because it is simply the addition of both or sum of both. So, here we are saying the 4 parameter model strain is simply the sum of strain in the Maxwell plus strain in the Kelvin. This we are getting from the kinetic equations. And once I superpose both these equations, I get the strain response in the 4 parameter model is given by these 3 terms. Okay. It is simply the strain response in the Maxwell and the Kelvin. But once we look closely at this equation, we will see that we can make a lot of physical interpretation. So, let us look at these 3 terms one at a time. So, first let us look at this term. What does this signify? So, this first term we get because of the free spring, where the modulus is E naught. So, what does it do? It gives an instantaneous strain, which means it gives you the elastic behavior. So, it is trying to give you the instantaneous elastic, because as we know elastic, when we apply a load, the response is instantaneous. Okay. The second term is called the delayed elastic behavior. The reason is because we have a spring as well as a damper parallel to each other. So, this damper does not give the instantaneous response, but given enough time, that is when it moves and gives you the additional strain. So, that is why it is called delayed elastic, and the reason why we call it elastic is because once we release the load, the spring which is in the Kelvin model brings it back to the original shape. And the last term here is coming from the free damper, and this represents the flow or the viscous behavior. So, now we have a physical interpretation of each of these terms in the creep response of 4 parameter model, but let us try to visualize this, how the creep response is. So, here we are looking at with time how the strain varies. So, we said at time t equal to 0 there is an instantaneous response coming from the first term. So, let us say that value is sigma naught by E naught. So, this is the instantaneous strain because of the creep load. But after that, if we wait longer, what happens is the delayed elastic, and if we wait even further, that is when we get the viscous behavior. So, meaning if we are looking at times going for t is equal to infinity, when t tends to infinity, the second term actually goes to 0, but when time tends to infinity, this term, the third term, goes to infinity. So, the response is something like this. So, initially it is non-linear, but later it becomes linear. It does not come to a constant, but it keeps increasing. It keeps increasing because of the third term, which is the viscous behavior, and this straight line has a slope which can be represented as sigma naught by mu naught. So, this term we are getting because of the free damper, and in between the initial nonlinear region is because of this delayed elastic behavior. So, if you think carefully, what do you think the 4 parameter model represents? Does it represent a thermoplast or a thermoset? So, we discussed that thermoplasts are the one where it gives infinite strain if we keep waiting, especially for creep load. The reason is because we said the molecular chains can now slide given enough time. Once they slide, it is basically flowing. So, this represents the 4 parameter model, which also is close to thermoplast. Thermoplastic. But in the previous slide we have looked at the 3 parameter model. What is the difference? In the 3 parameter model we only have the first 2 terms in the response, which means the elastic and the delayed elastic. So, let us see how it looks like. So, the response, the instantaneous response for the 3 parameter model will be the same because the elastic is still there or the free spring is there. The only difference here for a 3 parameter model is if we wait for very long times, it reaches a constant value. That constant value is coming from this delayed elastic. So, we are saying that it reaches a constant value and that constant value is so this is for the 3 parameter. So, this is for the 3 parameter model, and again if I ask the same question, which plastic does the 3 parameter model represent well? Is it for the thermoset or the thermoplast? The answer is thermoset, because we said because of the crosslinks, even if we give long times, the crosslinks have a limit until which it can stretch, after that it stops there. So, meaning that this 3 parameter model is good for thermosets. So, to summarize, what we have seen is the creep response for a 4 parameter model is simply the sum of strains in the Maxwell model and strains in the Kelvin model, and which is given by these 3 terms. We said the first term is the elastic term coming from the free spring, second term is the delayed elastic coming from the Kelvin model, and the last term is coming from the free damper. And we also showed that for a 4 parameter model the strain goes to infinity if we wait longer, but for a 3 parameter model it reaches a constant value. And regarding this thermoplastic versus thermoset, we said 4 parameter model better represents a thermoplastic, but a 3 parameter model better represents the thermoset. So, finally, in this video we have seen both the 3 parameter model and the 4 parameter model. For 3 parameter model we showed you the stress strain relationships, and then we derived the response for creep load. Later we also derived the response for creep load using the 4 parameter model, and we have seen that it can be written as simply a summation of the Maxwell model and the Kelvin model. So, with this we end this video. In the next video we will see how we can extend these discussions for a generalized and Kelvin models. See you then.